Welcome to this explainer. I am so incredibly pumped you're here today because we're going to unpack something absolutely fascinating. Have you ever just stopped for a second and wondered about the invisible mathematical brain that keeps our entire physical world from spinning completely out of control? I'm talking about the hidden code running behind the scenes of our modern infrastructure, making sure everything operates with just absolute pinpoint precision.
I mean, really, think about it. What actually keeps a massive AI data center? We're talking thousands of servers running red hot at maximum capacity? What keeps that from just completely melting down? Or how in the world does an oil refinery maintain highly combustible liquids at the exact right pressure? How do these massive, high-stakes environments maintain perfect stability when under immense, constantly changing pressure? Well, it isn't magic, it's math. Okay, let's dive right into this. The answer to that mystery is the PID controller. It stands for Proportional Integral Derivative, and it is hands down the most widely used feedback control loop algorithm in industrial automation. You can kind of think of this PID loop as the ultimate behind-the-scenes problem solver. Whether it's keeping a server rack intake temperature at exactly 22 degrees Celsius or controlling the speed of a massive cooling tower fan, a PID controller is constantly at work. It continuously calculates what we call an error, and then it immediately applies a corrected output to fix that error. Here's our roadmap for today's explainer. Number 1, anatomy of a feedback loop. 2, the present. 3, the past. 4, the future. 5, the art of tuning. And finally, number 6, we'll look at a data center rescue. All right, kicking things off with section 1, anatomy of a feedback loop, the 4 core components. So before we can really master the math, we've got to establish the basic vocabulary of automated control. To understand PID, you absolutely have to understand a closed-loop feedback system. Look at these 4 basic components. First up, the set point, or SP. This is your target goal. It's where you want to be. Think of it like saying, I want the room to be a crisp 22 degrees Celsius. Second is the process variable, or PV. This is your current reality, usually measured by a sensor. Let's say the room is actually sitting at 25 degrees. Third is the error. This is simply the mathematical difference between your set point and your process variable. You want 22, you're at 25, so boom, you have an error. And finally, the manipulated variable, or MV. This is the controller's actual action, like opening a chilled water valve by 45%. The whole shebang basically revolves around the controller continuously looking at the error and then adjusting the manipulated variable to change the physical world. Moving right along to section 2, present, past, and future, building the algorithm. Now this is where things get really cool. We're going to break down the 3 distinct mathematical lenses of the PID algorithm, and we begin with the P, the proportional term. I want you to think of this as the present. This first tool is super straightforward. It drives the output based strictly on the current size of the error. If the error is massive, it makes a massive correction. If the error is tiny, the correction is tiny. It literally just multiplies the error by a tuning game. It's reacting purely to exactly what is happening right now. But, and there is always a but, right? Check out the fatal flaw on the right side. Proportional control sounds totally logical, but it has a massive problem. It can literally never bring a system exactly to its set point. Why? Well, think of it like a giant puzzle. As your current temperature gets closer and closer to the target, the error obviously drops. And because the proportional term multiplies by the error, when that error drops near 0, the proportional output also drops to 0. So it just stops pushing entirely. As a result, the system always stabilizes just slightly short of the target. Engineers call this permanent gap steady-state error, or offset. So the crucial point here is that we clearly need something else to fix that permanent gap. Enter the I, the integral term. We like to call this the past. The integral term exists to eliminate that steady-state offset, and it does this by accumulating the error over time. It is pretty brilliant. It looks at how long the system has been stuck away from the set point. Even if the error is tiny, just a fraction of a degree, if it sits there for a long time, this integral sum just grows and grows. It eventually forces the controller to apply that little bit of extra power needed to push the system exactly onto the set point. But yeah, another flaw. It introduces something incredibly dangerous called integral windup. Imagine a huge disruption, like a frozen water valve. The integral term doesn't know the valve is physically stuck, right? It just sees the error persisting, so it blindly calculates and accumulates that error, pushing its output up to 100%. When that valve finally snaps open, that accumulated value is so massive that the system violently overshoots the target. It's a real issue. which is why engineers have to program in special anti-windup logic. And that brings us to our final tool, the D, the derivative term. This one represents the future. Think about it this way. If the proportional term is the engine and the integral term is that persistent push from behind, the derivative term acts as the brakes. And it does this by measuring the rate of change of the error. It basically predicts what's going to happen next. It watches how fast the process variable is rushing toward the target. If the temperature is suddenly dropping really rapidly, the derivative term sees that steep slope and actually subtracts from the total output, beautifully slowing down the approach to prevent you from blowing right past the target. But of course, it has a weakness too. Because derivatives measure sudden changes, they are incredibly sensitive to high-frequency electrical noise. If a sensor fluctuates rapidly by just 0.1 degrees because of some nearby electrical interference, the derivative term totally panics, calculating massive erratic output spikes. In tough industrial environments, this term often has to be heavily filtered, or sometimes engineers just turn it off completely.
Which leads us perfectly into Section 3, the art of tuning, finding the perfect balance. So we've got these three time-traveling mathematical terms, right? The ultimate challenge for any engineer is finding the absolute perfect balance between them. When you're configuring a PID controller, you generally see three main states of response. First is underdamped. This is chaotic. It's way too aggressive. The system shoots right past the target and oscillates wildly back and forth. Then you have overdamped. Now, this is safe, sure, but it is incredibly sluggish. It takes an unacceptably long time to finally reach the target. And finally, the Goldilocks zone, critically damped. This is optimal. It moves fast, it's safe, it smoothly decelerates, and it locks right onto the target with minimal overshoot. This is exactly what every engineer is constantly chasing. Let's see this in action in Section 4, the data center rescue, a real-world test. Okay, I want to set a really high-stakes scene for you here. Picture this. We're standing in a massive AI server hall. Suddenly, the servers initiate this massive compute load. Boom! An intense spike of heat is generated instantly. Our chilled water cooling unit, which is controlled by a PID loop, has to react right now to save these servers. At second 0, the sensor reads a huge 4-degree error spike. The proportional action immediately kicks in. The chilled water valve violently jerks open from 30% to 70%. Cold water floods in, fighting the heat. But as we hit minute 5, the room is stuck at 23 degrees. The P action just stopped pushing. But wait, the integral action has been watching. It realizes we've been exactly 1 degree too hot for 5 long minutes. So it steadily, slowly crawls that valve open from 70% to 75% to 78%. The temperature finally starts dropping perfectly. Now we're at minute 6. The temperature is plunging half a degree per second. It's totally going to overshoot, but the derivative action sees the future. It engages the brakes, easing the valve back just in the nick of time, and the temperature smoothly, perfectly lands exactly on 22 degrees. The servers are safe. And this brilliantly illustrates what we cover in Section 5, Summary of Loop Tuning Effects, the Master Matrix. This right here is where we synthesize everything we just learned into a true engineer's cheat sheet. Walk through this powerful matrix with me for a second. It shows exactly how adjusting these tuning parameters directly impacts the physical world. Look at this. If you increase the proportional gain, your rise time gets faster, but your overshoot increases. And while steady-state error decreases, it never quite hits 0. Now, if you increase the integral gain, you completely eliminate that steady-state error, which is great, but you increase the settling time and risk way more overshoot. And if you increase the derivative gain, you beautifully dampen the overshoot and decrease settling time, stabilizing the whole system. Balancing this entire matrix, that is the true art of industrial automation. You know, it is just truly incredible when you step back and realize that this elegant algorithm is silently running constantly in the background of our modern lives. From the cruise controlling your car to the massive data centers powering the entire internet, PID controllers really are these silent guardians of stability. So I'm going to leave you with this provocative thought to chew on. Look around you right now. Seriously, what invisible feedback loop is constantly measuring, adjusting, and controlling your world at this exact second? Thank you so much for hanging out with me for this explainer. Stay curious and keep looking for those hidden systems that make our world work.